The last image Cassini ever took was not of Saturn's rings. It was not of Titan or Enceladus or any of the moons it had spent 13 years studying. The very last photograph this spacecraft sent home was a view of Saturn's own atmosphere, pointed at the exact patch of cloud tops where 14 hours later it would enter at 77,000 miles per hour and burn apart. It photographed the place where it was going to die, and then it kept transmitting until the planet tore it to pieces. That is what happened on September 15th, 2017. And if you already know that story, hold on, because the part of this that almost nobody is talking about is not the ending. It is what has happened since. Scientists are still publishing new discoveries from Cassini's data right now in 2025 and at 2026, 8 years after the spacecraft ceased to exist. The data it sent home did not stop yielding results when the signal cut off. It kept giving. And what has come out of that archived data in just the last 2 years has changed the scientific consensus on one of the most important questions in the history of planetary science. Not gradually, fundamentally. Let me take you through all of it. Cassini launched from Cape Canaveral on October 15th, 1997. The spacecraft was the size of a school bus and carried 12 science instruments designed to study Saturn and its moons in more detail than any mission before or since. It launched as a partnership between NASA, the European Space Agency, and the Italian Space Agency. Attached to its side was the Huygens probe, a separate lander built to descend through the atmosphere of Saturn's largest moon, Titan, and transmit images from the surface. When Cassini lifted off, Google did not exist. The first Harry Potter novel had not been published in the United States. People were connecting to the internet through dial-up modems that took several minutes to load a single image. That is how long ago this spacecraft left Earth. It spent 7 years crossing the solar system using gravity assist from Venus twice, then Earth, then Jupiter, each flyby bending its path and adding velocity without burning fuel it could not afford to waste. It arrived at Saturn on June 30th, 2004, fired its main engine, and slipped into orbit. The mission began. Over the next 13 years, Cassini made 294 orbits around Saturn. It flew past the planet's moons 162 times. It took more than 450,000 images. It sent home so much data that scientists were still actively publishing papers from it when the mission ended, and have continued publishing ever since. Research based on Cassini observations appeared in journals in 2023 and 2024 and 2025, and it is still appearing now. A spacecraft that no longer exists is still doing science through the data it left behind. That fact is worth sitting with before we go any further. What Cassini was arriving at in 2004 was not simply a planet. Saturn is a system. A planet with 145 known moons, each one its own environment with its own geology and its own history. A set of rings made of billions of individual pieces of ice and rock, some no larger than a grain of sand, some the size of a house, all orbiting in a flat disk that stretches hundreds of thousands of miles across. From Earth, through a telescope, Saturn looks peaceful. Up close, Cassini found something else entirely. Wild, strange, violent, and full of surprises that nobody had predicted. The biggest surprise of all came from a moon nobody was specifically watching. Enceladus is small, roughly the diameter of England from north to south, covered in white ice, orbiting Saturn quietly. Before Cassini arrived, it had a reputation as a dead, frozen rock. A moon without particular interest. Scientists expected to confirm that and move on. What they found instead, during the first close flyby in 2005, stopped the mission team completely. The spacecraft's magnetometer detected a disturbance in Saturn's magnetic field near the south pole of Enceladus. That kind of disturbance has only one explanation. Something was being ejected from the moon into space. Cassini turned its cameras toward the south pole and found geysers. Enormous jets of water vapor and ice particles blasting through cracks in the surface at nearly 800 miles per hour, shooting hundreds of kilometers up into space before dispersing into Saturn's outermost ring. Not one geyser, multiple simultaneous plumes erupting continuously from a set of parallel surface fractures that the team eventually nicknamed the Tiger Stripes. The moon was not dead. It was erupting, and nobody had predicted it. The obvious question was immediate. Where was all this water coming from? Cassini answered that question across a series of increasingly close plume flybys through the erupting material just 49 kilometers above the surface, and sampled what was actually inside those jets. What the instruments found built a picture unlike anything scientists had seen before in the outer solar system. The water was salty, with a salt content comparable to Earth's oceans. There were organic carbon compounds. There were silica degrees Celsius. On Earth, that process happens at hydrothermal vents on this food. Certain ancient microbial organisms consume hydrogen and carbon dioxide and release methane as a metabolic byproduct. It is called methanogenesis, and it is considered one of the oldest biochemical processes in the history of life on this planet. Cassini confirmed that Enceladus has a global liquid ocean beneath its ice shell, not a liquid by the heat generated as Saturn's gravity constantly squeezes and stretches the moon's interior as it orbits. That process is friction deep inside the rock, warming an ocean in total darkness, 900 million miles from the sun. And then the data from the archive started arriving. In 2023, a team led by Frank Postberg at Freie Universität Berlin published an analysis in the journal Nature based on data collected by Cassini's cosmic dust analyzer instrument during flybys of Saturn's E ring, the outermost ring that Enceladus itself feeds with its constant plume ejections. They examined 345 ice grains sampled from that ring. In 9 of them, they detected sodium phosphates, phosphorus, chemically bound in water-soluble form, ejected directly from Enceladus's subsurface ocean and captured in the archive of a spacecraft that had been gone for 6 years. The concentrations were, some estimates placed the figure at thousands of times higher. Membranes, to bones, to every biochemical structure that life on Earth has built over 4 billion years. It is, by mass, the 12th most abundant element in Earth's crust. And until the 2223 Cassini paper, it had never been directly detected in any ocean beyond Earth. Not once, in any mission, anywhere. Enceladus was the first. And the measurement came from data collected by Carolyn Porco, a planetary scientist who served as the imaging team leader for the Cassini mission, called Enceladus the most promising place, the lowest hanging fruit in our entire solar system to search for extraterrestrial life. She was not speaking loosely. She was summarizing what the accumulation of Cassini results had built toward. An ocean beneath an ice shell, hydrothermal vents on the seafloor producing molecular hydrogen, organic compounds erupting continuously into space, salty water chemically similar to Earth's oceans, and now phosphorus at concentrations that dwarf what Earth's ocean contains. And then October 2025 arrived, using archival Cassini data, this time focusing on ice grains collected during close Enceladus flybys rather than from the E-ring. The distinction matters because ice grains circulating in the E-ring have been exposed to radiation and space weathering for potentially centuries before Cassini collected them. Complex organic molecules that had not been identified in any previous analysis of the Cassini plume dataset. The molecules were not simple. They belong to classes of compounds that on Earth appear as intermediate steps in the chemical chains that lead from basic organic chemistry toward the more complex molecules that life requires. Not life itself, not the molecules of life directly. The chemical road that on Earth leads toward biology. And Enceladus's ocean is apparently actively running those reactions right now. The dark, under the ice, whether we are watching or not. Cassini was detecting samples from Enceladus all the time as it flew through Saturn's E-ring, Kawaja said. We had already found many organic molecules in these ice grains, including precursors for amino acids. What the 2025 analysis added was the demonstration that the fresh plume material, the direct product of whatever is happening at the ocean floor, carries complex organic chemistry at a level that exceeded what the earlier dataset had revealed. Complex chemical reactions are actively occurring in Enceladus's subsurface ocean. The finding strengthens the case that the moon's underground environment hosts conditions analogous to those in which life arose on Earth. The European Space Agency announced in 2024 that Enceladus was one of its top targets for a future mission. Studies for a spacecraft capable of orbiting the moon and landing on its south polar region to collect samples directly from the plume material have already begun. The scientific case for that mission was built entirely on Cassini data. Every piece of it, the global ocean, the hydrothermal vents, the organics, the phosphorus, the fresh complex molecules, all of it came from one spacecraft that ended in 2017 and whose archive is still yielding results in 2025. That is what it means for a mission to keep doing science after it ends. Then there was Titan. If Enceladus was the scientific earthquake, Titan was the revelation that changed what we think a world can be. Saturn's largest moon is bigger than the planet Mercury. It has a nitrogen atmosphere denser than Earth's, an orange, smoggy canopy so thick that for most of the history of planetary science, the surface was completely invisible from space. On January 14, 2005, the Huygens probe separated from Cassini and descended through that atmosphere on a parachute over roughly 2.5 hours, transmitting measurements and images as it fell before landing softly on the surface and transmitting photographs from the ground. It was the first soft landing on any body in the outer solar system in the history of space exploration. Huygens looked around and found pebbles. Rounded, smooth pebbles of the kind that form when liquid flows over rock for long periods of time, abrading the edges, shaping the surface. The liquid on Titan is not water. At Titan's surface, temperature of around minus 290 degrees Fahrenheit, methane behaves the way water behaves on Earth. It evaporates off the surface, forms clouds in the atmosphere, falls as rain, carves channels through the landscape, and collects in rivers that flow into lakes and seas. An entire hydrological cycle running on a completely different chemical, in a world where the sun appears as nothing more than a very bright star, 9 times dimmer than it appears from Earth. Cassini mapped Titan's lakes and seas over 13 years using radar that could penetrate the orange haze and resolve the surface below. What it found was not puddles. Kraken Mare, the largest liquid body on Titan, is bigger than the Caspian Sea. It is filled with liquid methane and possibly liquid ethane. Some lake basins were so deep that Cassini's radar could not reach the bottom. Sand dunes, made not of silica but of complex organic compounds, cover vast stretches of the landscape. The atmosphere is thick with organic chemistry, molecules that drift downward over billions of years and accumulate on the surface in layers that scientists call tholins. Pre-biological chemistry, building up slowly, one molecule at a time, in the cold dark of a world that looks in many. Ways like a frozen photograph of what early Earth might have looked like before life changed everything. There is a mission coming. NASA's Dragonfly is a rotorcraft, roughly the size of a large car, designed to fly through Titan's thick atmosphere from site to site and directly sample the chemistry at each landing location. It is targeting launch no earlier than 2028. Its destination is the most chemically interesting surface in the outer solar system, a world that Cassini spent 13 years mapping, and that returned enough unanswered questions to justify a rotorcraft mission capable of tasting the surface directly. Saturn itself yielded surprises that nobody expected. The rings turned out to be wrong in the most fundamental way. For most of the history of planetary science, the rings of Saturn were assumed to be ancient, as old as the solar system itself, formed 4.5 billion years ago from the same primordial disk of gas and dust that made the planets. That assumption sat unchallenged for decades. Nobody had a way to test it. Then, Cassini's Grand Finale provided the test. In its final months, instead of continuing to orbit safely outside the ring system, Cassini dove through the bone 200-mile gap between Saturn's innermost ring and the planet's cloud. TOPS, a region no spacecraft had ever entered, a region scientists genuinely were not certain would be survivable. The first dive worked. The gap was almost empty, far less debris than the models predicted. And the gravity measurements taken during those close passes, Cassini flying near enough to Saturn to detect subtle variations in the planet's gravitational field with unprecedented number that came back was shocking. The rings are far less massive than any 100 million years. Not 4.5 billion, 10 to 100 million. The rings that define Saturn in every image we have ever taken of it, the rings that every child recognizes, appeared somewhere around the same era that dinosaurs walked the surface of this planet. Before that, Saturn had no rings, and they are disappearing. Material falls into Saturn's atmosphere at a rate that suggests the ring system could be completely gone within the next 100 to 300 million years. We live at a specific, brief moment in the histories of this solar system when Saturn happens to have its rings. Before us, nothing. After us, nothing. Right now, for this particular eye blink of cosmic time, they are there. And then the magnetic field. Every planet that generates a magnetic field has one that is tilted relative to its rotation axis. Earth's is offset by about 11 degrees, Jupiter's by about 10. That tilt creates a wobble as the planet rotates. And that wobble is one of the primary tools scientists use to determine how fast a planet spins internally, independent of its surface weather or cloud movements. Cassini measured Saturn's magnetic field in extraordinary detail during the Grand Finale dives. The result was the most confusing measurement of the entire mission. Saturn's magnetic field has no detectable tilt. It is aligned with the rotation axis to a degree of symmetry that current physics says should not be stable. A perfectly aligned magnetic field like this should not be able to sustain itself over geological time. And yet there it is, perfectly symmetrical, defying the models. The direct consequence is that without a measurable wobble, scientists cannot use the standard technique to determine Saturn's interior rotation rate. After 13 years of the most intensive Saturn study ever conducted, we still do not know how long a day is on Saturn. We cannot measure it. Saturn is keeping a fundamental piece of information from us, and Cassini could not unlock it. On September 13th, 2017, 2 days before the end, Cassini pointed its cameras one final time at the moons and the rings, and the planet it had studied for 13 years. It took a farewell image of Titan. It looked one last time at Enceladus. It photographed Saturn's rings and caught a tiny moon called Daphnis sitting in the Keeler Gap, small enough that it creates wave patterns in the ring edges as it orbits, like the wake from a boat in still water. And then it took the very last image of all, a monochrome photograph looking at the sunlit face of Saturn, pointing directly at the precise location in the atmosphere where it would enter 14 hours later, a picture of where it was going to die. Then it turned itself to increasing atmospheric resistance, continuing to transmit data. For 91 seconds, it held. Then the thrusters lost. The spacecraft began to tumble. The signal cut off. Somewhere in the cloud tops of Saturn, at temperatures reaching thousands of degrees, a machine the size of a school bus that had launched when Google did not exist dissolved into a streak of light and became part of the planet it had spent 13 years orbiting. At JPL in Pasadena, the room fell silent, and then people began to cry. Scientists who had built instruments for this mission, who had devoted careers to it, who had been alive for the entire span of it, sat at their consoles and wept. They had chosen this ending deliberately. Cassini was directed into Saturn's atmosphere rather than left in orbit specifically to prevent any possibility of an accidental collision with Enceladus or Titan, worlds that might harbor life, worlds that must not be contaminated by Earth biology before they can be properly searched. The ending was chosen to protect the question Cassini had raised, 83 light minutes from Earth. By the time that signal arrived, and people in the room, the ending was already past tense when they learned it had happened. Saturn kept the actual moment. No camera saw it. No recording exists. Just a machine that had been alive and transmitting for 20 years. And a planet, finally together. The data it left behind has continued producing results ever since. The phosphorus paper came in 2023. The complex organics paper came in October 2025. More papers are in progress right now, working through observations that have been sitting in the archive since before the mission ended. Cassini stopped transmitting 8 years ago. Its science has not stopped. There is a question sitting at the center of all of this that Cassini raised and that nobody has yet answered. A small moon, smaller than England, covered in white ice, generating heat from inside through nothing but gravity, maintaining a global ocean in total darkness, erupting that ocean's chemistry continuously into space, where a spacecraft flew through it and tasted salt and organics and hydrogen and phosphorus at concentrations that dwarf what Earth's own ocean contains. Is something alive in that ocean right now? Not in some distant galaxy, not around some star 40 light years away, in our own solar system. Around the planet, you can see from your back garden on a clear night with nothing more than a basic telescope. That question, raised by Cassini in a flyby that nobody saw coming, of a moon that nobody was particularly watching, is now considered by planetary scientists to be the most important open question in astrobiology, and the data that raised it is still arriving. Years, that is what Cassini's final images actually mean, not the ending. The question that is still being asked because of what the ending left behind.